I'm Eli Dourado. I'm thrilled to be here, and I think there's no better time to talk about next generation geothermal than right after Jason, because next generation geothermal is like nuclear without all of that hassle that he just talked about. So I like bar charts like this that show the size of the energy reservoir. So geothermal is the big bar, and the little bar is fossil fuels. So that's how much, it's 4 orders of magnitude bigger energy resource than fossil fuels. It's effectively limitless. With next generation technologies, we do need some energy, some breakthroughs, some experience, but it's available anywhere in principle. It's baseload energy. Could be cheap. And it's, best of all, not highly regulated. So I'm going to talk about 4 different concepts for how we could do next generation geothermal, but they all basically, they all essentially do the same 3 steps. They locate and access heat, they transfer that heat to a working fluid and bring it to the surface, and then they exploit the heat energy at the surface. That second step, that transferring heat to a working fluid, like that's the hard part. That's the thing that people are trying to figure out the best way to do it. So concept number 1 is called enhanced geothermal systems. And this is like, very similar to conventional geothermal, if you're familiar with that at all. But it starts with you drill an injection well, and you go deep until you get heat, and you inject water into that well. You drill another well, a production well, and that's the one that steam is going to come out. And then the question is like, how do you get the water from the injection well to the production well? Well, you need a porous environment down here. So if natural permeability doesn't exist, you create it through fracking. And so the water comes in, it's hot down here, it's seeping through the fractures, the high surface area, it's acquiring a lot of heat through that process, and then it comes out as steam, and you use it to power a turbine. So you engineer basically a hydrothermal resource. So the downside is with current tech, you're limited by location. It's got to be, you can go a little deeper than what's possible with conventional geothermal, but not that much deeper. And the other issue is that with the temperatures you're going to be accessing with current tech, you're limited to the energy density of subcritical steam. So the supercritical, subcritical distinction in working fluids really matters. When you get to supercritical conditions, you should be thinking like a 5 to 10x efficiency improvement. So you accumulate more energy in the fluid, and then it's also more efficient in generation. And there's a company called Fervo that is doing this approach. They just raised a B round and signed a deal with Google. So they're making progress. Second concept is called closed-loop geothermal systems. And so in this case, instead of having an injection in a production well that is connected with an open reservoir, you have a closed loop. You pump the water down in one place, flow it through pipes at depth to acquire heat, and then bring it back up in another spot. And so you're acquiring the heat in this horizontal segment at depth. The advantage of this is that you can use a fluid other than water, which can become supercritical at the temperatures that we're talking about. So you could use isobutane or CO2. Those become supercritical, so they're higher enthalpy, can transfer more heat. The downside of this approach is that you have much lower surface area of the pipes. You're limited to the surface area of the pipes, and as a consequence, the pipes at depth have to be, those horizontal segments have to be very long, and horizontal drilling is still really expensive. Nevertheless, there is a company that is trying this approach. Their name is Ever. Concept number 3 is called heat routes. And the idea here is you create a single vertical well that has a pipe and pipe, so it's going to be circulating fluid from the top all the way down to the bottom and then back up through that single shaft. But the trick here is that after you drill that vertical segment, you frack downwards, and you create a fracture network that looks like a root system. And you fill that root system from here on down with a convective and conductive fluid, and that lets you draw heat up from deeper than you were able to drill before. So at the base of the well, all that heat is concentrated and exchanged into the working fluid, and it comes back up. You can still use your supercritical fluid because the main part of the thing is a closed loop system. And a huge advantage of this is that it's very high reproducibility. All you have to do is drill deeper at any given site. You don't have to, there's not as much exploration risk. You just drill deeper until you hit the right conditions, and then you're able to make your well work. The downside of this is because you're limited by, you have just one vertical shaft that's at relatively low flow rate, so you're talking about maybe 10 megawatt per plant. So that's kind of low power output. Maybe that doesn't matter if you can stamp out a lot of these in sort of cookie cutter fashion, just make a lot of them, and that could work. So there's a company called Sage Geosystems that raised an A round earlier this year. They're off building their first well demo that is exactly like this. The fourth concept is supercritical EGS. So that's like the first one, that's like EGS. But the difference is you use some technology breakthrough to go a lot deeper and to get access to 500 degrees C temperatures. And if you can do that, then some magic starts to happen. So this does rely on new technology. You need some new way to be able to drill more deeply to get to that really high temperature. And the solutions that people talk about are plasma drilling and millimeter wave directed energy. A huge advantage of that temperature is that you're producing steam, supercritical steam, so you can pipe that into existing coal turbine equipment. So you can imagine putting one of these systems at a coal plant. So your production wells are at the coal plant, and you're producing supercritical steam at the surface, and you just pipe that straight into the coal generator that is being shut down, would otherwise be shut down, and you get electricity. So it's like you get the primary energy for free. This is also one that only relies on vertical drilling. You could potentially it could be very high reproducibility in the sense that anywhere on Earth you could do this if you could drill deeply enough. So it could be very cheap. There's a company at MIT that spun out of their plasma physics lab that is trying to do the millimeter wave version of this. So policy barriers. Nothing like fission. It's suboptimal, but not a deal breaker. And I'll highlight two issues. So one is permitting on federal land. So if you want to drill a oil and gas well on federal land, you get approval in about 2 weeks. You don't have to go through a big environmental review process. If you want to do a geothermal well, you have to go through environmental review, and it takes about 2 years. So 2 weeks versus 2 years. Why is this? It's because the oil and gas industry lobbied for an exemption, or for a categorical exclusion to NEPA, and they basically, that's just, the geothermal industry hasn't been organized enough to ask for that. And why does this matter? It's because the lowest hanging fruit for energy is all in the West, right? And that's where a lot of the federal land is. So it is very attractive as a starting point to go in those places. The subsidies for wind and solar are more generous than for geothermal. That's like another case where those lobbies have been much more effective. So I think there's really 5 buckets of technology breakthroughs that we need to make a lot of progress on this next generation geothermal. The first one is in resource characterization. So de-risking the drilling of individual wells by knowing where the heat is below the ground. So you could use big data to do this. You could use new sensors to do it. And probably you want to eventually use both. Another really important one is hardening the existing drilling equipment that exists for the oil and gas industry. So these rotary drills have a lot of sensors and electronics on them. They are not optimized for the conditions that you would reach within a geothermal project. So you need to basically do some technology transfer, probably from the space industry, to harden the electronics so that they would work in geothermal conditions. The non-rotary drilling concepts, like the millimeter wave, like the plasma bit, maybe also some air hammer and mud hammer stuff that would let you drill deeper and cheaper. For the two closed loop systems, I think specialized equipment for supercritical fluids, turbines, but also casings and coatings that would be used in the wells. And then finally, standardization of the turbines to drive down the cost of manufacturing. So I think the number one thing we need to do to unlock progress in geothermal is get going, just work down the learning curve. We need to deploy a lot of this. Geothermal is basically a rounding error right now. Every project is bespoke, and sort of just increasing output in the industry is really important. And I think the goal should be at least multiple terawatts by 2040 produced by geothermal.